Welcome. Our topic was the sensitivity analysis of energy consumption of an electric vehicle with different maximal acceleration values. First, we are going to talk about the simulation framework called Flow, which we use to create this homework. Then the actual environment will be presented, how the network and the vehicles looks like. After that, we will talk about how we process the data came from SUMO and how the results looks like. Flow is created to fill the gap between modern machine learning and complex control problems in traffic. It is a computational framework for traffic microsimulation with reinforcement learning methods. It was developed at University of California, Berkeley. The implementation builds upon SUMO and its Python API called Tracy for vehicle and traffic modeling, RAL-lib or stable baselines for reinforcement learning, and OpenAI Gym for the Markovian decision process. Scenarios are defined within the Markov decision process framework. Flow's basic units are modules, which can be composed to comprise scenarios including networks, actors, observers, control laws, metrics, initializations, and additional dynamics. Although Flow was developed for machine learning purposes, it can be used in our task with some modifications as well. The environment was a three-lane highway where the Ego vehicle was added as an initial vehicle, and traffic vehicles were coming into the environment with a specified frequency flow rate. Ego drives into the highway from a ramp with slower velocity to ensure there will be vehicles in front of the Ego all times. The highway contains only two lanes before the ramp to avoid complicated merging of the Ego. The first task was to create the highway itself. It was done in Highway Network class, which inherited from Flow's base network class. It contained the generation of nodes, edges, and specification of roads. Edge 0 was the entry point of the inflow vehicles, which initial lane and speed were randomly chosen. Edge 1 was the merging section of Ego, which was coming from the ramp, and from there, the highway was 3-lane wide. Edge 2 was a 20-kilometer long straight section, which was the main section of the measurement. Ego was based randomly on Edge 4, which was a parallel road section with Edge 0. The next task was to create the vehicles. Originally, Flow not support different vehicle types and emission classes. It uses its default values. This issue was fixed by adding new variables to the generated module, which override the default values. The Ego vehicle was an electric vehicle, and the traffic vehicles were traditional internal combustion engine vehicles or trucks. There were three types of them in this simulation: RL or Ego, and Flow vehicles, which could be passenger cars or trucks. Some information can be found about them in this table. For example, the desired velocity of Ego was a fixed value, 35 meters per second, but the desired speed of Flow vehicles were generated randomly within a range. In the last days, we updated the simulation with new parameters to make it more colorful and diverse. The Flow passenger vehicles class was divided into three subclasses: sedans, wagons, and motorcycles. The truck class was divided into trucks and buses. That different lane change models, emission classes, and parameters were added to different vehicle classes. This can be seen only in the code and on the attached video, because we didn't have time to run and evaluate all simulations again with these new parameters.
Once we ran our simulation, we have a huge table that contains a lot of unnecessary information, and we have to choose what is important for us. Doing it manually would be time-consuming for all the cases, so we wrote a Matlab script. It chooses Ego vehicle data from the table and computes acceleration, distance, and total consumption. On this slide, you can see some plots from a simulation case. The acceleration limit was 4 meters per second squared. High consumption peaks occur at high accelerations. For example, here you can see the peaks, and here you can see the acceleration peaks. And these peaks occur at lane changes. For example, here you can see that at each lane change there are some red spots, and also there is high consumption when the cruising speed is high. For example, here you can see here how the current consumption varies with the speed and with the acceleration. Mostly we travel at constant speeds, and we only have 5 data points with the acceleration limit. As a conclusion, increasing acceleration limit might reduce energy consumption. It results in higher acceleration peaks, but these peaks occur for a shorter period of time, so the cruising speed is attained much earlier. The overall consumption was influenced more by the cruising speed and by the number of overtakes on the route.